Pause the recorder. Yes. So I thought is that we have to create our opportunities. Some things will not fall in our laps. It's a commentary that I don't like, but it's one that needs to be said. Maybe we just need to be un-Jamaican as much as possible. That's not a good thing, but hey, it's what it is. Okay? All right, so let's get cracking with today's list. So last week we looked at this circuit. We had 3 resistors connected across a source E. And we had a current I leaving the source. And then we had currents I1, 2, and 3 going through the resistors. And based on Kirchhoff's current law, this would be our node. Our node is right here. Okay. And of course, all of this would be a node also. All right. So we basically have 2 nodes in this circuit. So what we know from Kirchhoff's current law is that the sum of the currents entering the node is equal to the sum of the currents leaving. So the current entering this node would be I. Yeah? We're going to call that IT. And the currents leaving the node would be I1, I2, and I3. Yes? And of course, from what we know from Ohm's law, we know that I is equal to V over R. Okay? Now, before I go into that, just going back to what we said last week. We talked about voltage drop, and we know that we'd experience a voltage drop when the current passes through a resistor. Agreed? So from the source flowing towards that node, obviously we have no resistance, so we wouldn't have a voltage drop. Fair enough? So there's no voltage drop between these 2 points. So obviously the potential at A would be the same at that point. And the potential at B for the source will be the same at this point. So in other words, the potential difference for the source, which of course we know as voltage. Remember, the voltage is the difference in potential between 2 points. Yes? So I'm using everything that we said last week. So because there's no voltage drop, we have the potential at the top of the source being the same at where I indicated for the node of A and B. So it means that the potential difference across each of those resistors would be the same. Okay? So in the past, you would have simply been told that, well, I'm going to use the term, even though I didn't want to get there yet, but we have simply been told that resistors in parallel, the voltage is the same across them. Isn't that so? So the principles that we learned last week is what I'm now applying to show why it is that we say if the potential is the same across them, then they are in parallel. Are we clear? All right. So I is equal to V over R. And based on what we just outlined, we know that the potential difference across each of these resistors will be the same. So it implies that I1 would be equal to E over R1. I2 would be equal to E over R2. And I3 would be equal to E over R3. All right. If we simplify that, we therefore get that I is equal to E over R1 plus E over R2 plus E over R3. All right. Which implies that E into 1 over R1 Okay. Or I over E, which obviously is the reciprocal of the resistance. So IT over E would be equal to 1 over RT. Yes. I don't have any raise function on this. Anyway, is equal to 1 over R1 plus 1 over R2 plus 1 over R3. All right, which implies that for N resistors, and I said resistors, but I'm going to change that to resistances. Okay, so for N resistances in parallel, parallel, 1 over RTN is equal to the sum from I equal 1 to N of 1 over Ri. All right. So if the resistances are in parallel, then 1 over Rtn is equal to the sum of the reciprocal of the resistances. Okay? And I'm very deliberate in what I say in terms of resistances. So two things we saw with the resistors in parallel. So last week we said that resistors are in series if the current, and we also, before I get to that, we also said that we're going to be talking about the current and what the current is doing in order to represent all that we're going to be talking about, you know, in terms of our circuit analysis. Good? We spoke about current. Never forget that. So for series circuits, we said that if the current leaving one resistance is the same current, not equivalent, but the same current entering the other, then they are in series. Good? Now for parallel, talking about current, we're now going to say that if the current entering the node connecting the two elements, then they are in parallel. What did I just say? That's wrong. Anyway, let's go again. If the current entering the node which connects both elements divides between the elements, then yes, they are in parallel. That's the correct thing. I kind of ate a bit of it. So I come back to our circuit. We have a current I, and it's entering node A. Yes? The current entering node A divides between R1, 2, and 3. Would have changed the English. Normally would have said among, but anyway, divides between those three. Yes? Then 1, 2, and 3 are in parallel. So I want you to know, because I know, I mean, I've heard persons in the high school system talk, and they use terminologies, or they use definitions such as which refers to the orientation of the resistors for them being in parallel. We have to destroy that notion. So in determining what is in parallel with what, you need to look at what is happening to the current as it enters the node that connects those resistors or resistances. Are we clear? Is that confusing enough? No?
Yes, sir.
Should I confuse it a little more?
Not clear, sir.
Yes, sir. All right. Okay.
You want to confuse it?
I'm just checking. I'm just checking. So for this circuit, based on what we just said, obviously these resistors are in parallel. Yes, because this current is entering this node, which connects all three elements. And that current is dividing between R1, 2, and 3. All right? And so the question is, determine the total current being supplied. Determine the current being supplied by the source, given that the source voltage is 60 volts. All right? And so we can take different approaches for this. We can find the currents going through each branch. So we know that I1 would be equal to 60 over 30, which gives us 2 amperes. We know that I2 would be equal to 60 over 10, which is 6 amperes. And of course, I3 would be equal to 60 over 15, which is equal to 4, which implies that IT is equal to 2 plus 6 plus 6 plus 4, which is 12 amperes. All right. Or we can say that RT, or 1 over RT, is equal to 1 over R1, 2, 3, which is 1 over 30, 10, 15. Yes, the same there, 30. So we have 1, 5, 2. Yes, 1, what am I? 1, 3. Why? This is not my morning. 1, 3, 2. Yes, which is 6 over 30. Okay, which implies therefore that RT is equal to 5 ohms. Or IT is equal to E over RT, which is 60 over 5, which gives us 12 amperes. All right, so whichever method you feel is easier, use it. All right, you okay with that?
Yes, sir.
Yes, sir.
So we're going to introduce something else. So the first part of the question was for the total power. The next part of the question, total current. The next part of the question is for you to determine the total power dissipated or total power supplied by the circuit and the power dissipated by each resistor. So we want to find the power supplied and also find the power dissipated by each resistor. All right. So Clark, please put your camera on. Thank you. All right. Now, we hadn't discussed it before, so we introduced another formula. So power is given by voltage times current, V times I. All right. However, again, from Ohm's law, we know that I is equal to V over R. So if we substitute for I in the power equation, then it means that P is equal to V times I being equal to V over R. So power is also equal to V squared over R. Yes? And also, if we rearrange the Ohm's law equation, we have that V is equal to IR. Again, making the substitution for the power, P would be equal to IR times I, which means that P is also equal to I squared R. All right, so with respect to resistors, P is equal to IV, it's equal to V squared over R, and it's equal to I squared R. All right. Okay, now, before I go any further, I want to go back to the circuit a bit. Let's go back to the circuit. Based on these currents, yes, let's call this node A. And of course, we have node B at the bottom, yeah? Based on these currents, in what direction would they be flowing? Just give me in terms of the nodes. In what direction would they be going? Come on, you all should answer at the same time.
A to B, sir.
A, B.
A to B. So the current should all be going down. Okay. All right. Now, Mr. Clark, since you gave me the answer, let's continue with you. In terms of polarities for the resistors, yes?
Yes, sir.
Which end of the resistor will have a plus sign?
A, sir.
All right. So we'd have the plus signs up here. All right. Beautiful.
Yes.
Now, in terms of the voltage drops based on these currents, yes? In going in that direction, would I be experiencing a voltage drop or a voltage rise?
Voltage
A
drop.
drop.
All voltage drops. Beautiful.
Right.
Everybody comfortable with that? No question
Yes.
on that.
Yes, sir.
All right, good. So let's come back to our power now. We have our circuit, we want to find the powers. So we know that P is equal to VI. So the first question is the power supply. Now, in supplying power, we expect that to come from a source, eh? So we're talking about the supply of power. We are looking at any entity or any component within the circuit that is delivering current to the system. All right? Now, let's do something practical. When you're charging a battery, yeah, or when you're giving somebody a jump start, haven't seen that in a while, but anyway, let's assume that we have done it, yeah? You're giving somebody a jump start. How do you connect the batteries? How do you connect the jumper cables?
Positive and negative to negative.
So positive to positive, negative to negative. Excellent. Now, in terms of current flow, which of the batteries you believe would be putting out current and which one would receive current?
So the one doing the jumping will give off the current, while the one getting jumped will be receiving the current.
Well, it's the car that is getting jumped, but
You mean like higher
so the one
potential?
that is supplying the current would be the better battery, right?
Yes, sir.
So it is supplying what? It's supplying electrical energy, eh? I'm still talking to you, Mr. Bernard.
Yes, sir. Yes, sir.
So it's supplying power. That's all?
Yes, sir.
So what is it that the other one is doing?
Receiving it.
It's receiving power, or it's absorbing power. It's absorbing energy. Is
Yes,
that
sir.
so? All right. Now I
Yes.
want you to think about the plus signs because we said that both of them had their positives connected to each other. And they also
Okay.
had their negatives connected to each other. So the one that is supplying power, the current is leaving which of its terminals?
Positive.
And the one that is absorbing power, the current is, how is the current flowing with respect to its positive terminal?
So it's going into the positive and coming out the negative.
Beautiful. And that is what we are going to use in terms of determining whether or not a component is absorbing or producing power in your electrical circuit.
All right.
So you know that practically, and it's simple. And Mr. Bernard shaking his head because I'm wondering why I take 2 minutes to explain this. Right? And he's saying, why don't I get on with the lesson, right? But it is
Sure.
important that I spend the time, Mr. Bernard.
All right, sir.
Yeah. So I was right in terms of what I assumed about you just now,
Sir,
Okay.
what was that assumption, sir?
that I'm wasting time. But anyway, we move on. So let's go back to the circuit now. The first question was, what is the power supplied? If we look back at the circuit, within the circuit, what is it that is supplying power?
Battery.
The battery.
And the 60-volt battery. Right.
So we have the voltage and we have the current. So we can now say power supplied which is equal to V times I is equal to 60 times 12.
60 times
720
12.
watts.
So we have 720 and the units for power is watts.
Right.
So that's the power supplied. Now going back to the same battery example, we are now asking for the power dissipated, and we can use dissipated and absorbed interchangeably. Yeah? So when we say power dissipated, we're talking about power absorbed. Yeah? Now you look back at the circuit based on the current, we see the polarities on the battery, on the resistors. So we can safely say that all the resistors are absorbing energy. They're absorbing power or they are dissipating power. But I'm telling you from now, it will not always be like this. All right? I'm just putting that out there. We're moving right along. So in terms of absorption of power or dissipation of power, for resistor R1, the power absorbed would be equal to, now what's the voltage across R1?
60 volts.
60. And what's the current? Oh, Mr. Bernard, you didn't write down anything.
Sir, me just calculate it on the calculator and then you never write it down.
Oh. You see why I need the camera now? Because I understand what is happening.
All right, sir.
It's important. Remember what I said last week? And I'm going to repeat myself ad nauseum. Well, I was about to say I was going to haunt you, but that may not be a good thing. Right? But I'm going to keep repeating these principles in terms of your approach to work. All right? I know I'm going to bore you this week because what we're going to do is so simple, but I guarantee you, 10 weeks from today, everything that I'm talking about now, you'll realize how important it was.
All right, sir.
Thank you. So the current there is 2 amperes. So we get 120 watts. For resistor R2, the power absorbed, 60, and the current was 6. So we get 360 watts. And for R3, the power absorbed, 60 by 4, and we get 240 watts. All right, so the total power absorbed is equal to 720 watts. All right, now here's the kicker, students. Yes, this is a simple question, but here is the kicker. You note that the power supplied was also 720 watts. All right? And I say to you the same thing I've said to every group of students I have taught networks. Everyone, bar none. You can't call me and ask me certain questions. You can't call me and ask me. Worse, you can't call me at the time that you're studying because you'll be calling at night. Right? And if my phone ring after 9, I don't answer it. So you see, while you're studying and you want to verify whether or not what you have done is correct, regardless of how complex the circuit looks. Can I say it any stronger? Regardless of how complex the circuit is that you are analyzing, to determine whether or not your analysis is correct, you do what is known as a power balance. Power balance. And that power balance is that the sum of the power supplied must be equal to the power absorbed. You don't need to check with your brethren. You don't need to check with the lecturer to find out whether or not the answers you have gotten is correct. What you do is to conduct a power balance. You look at the power absorbed, you look at the power supplied, and they must be equal. Enough said. Any questions? Are we moving on?
No, sir.
No, sir.
Okay, so we move back to a circuit that we looked at before, and we just want to introduce a couple of principles. So we know that this is a series circuit. We have I, yeah, that's IT. Of course, we have R1, R2, and R3. We know that RT was equal to R1 plus R2 plus R3. We also know that IT is equal to VS over RT. Fair enough? And when we looked at the analysis in terms of Kirchhoff's, we know that VR1 was equal to IT times R1. But IT, in terms of the supply voltage, is VS over RT. So it means that VR1 is IT, which is VS over RT, times R1. Or in other words, VR1 is equal to VS R1 over RT. This, ladies and gentlemen, is known as the voltage divider rule. All right? So that's your voltage divider rule. So in general, everybody have that? All right, so usually I give one warning. So this is the one warning. So all those persons without their cameras on, put them on now I'll check back in another 5 minutes and then I'll start removing persons from the room. All right? Okay, so moving right along. In general, for N resistors or resistances connected in series, yes, the voltage across a resistor X, a resistance X, is given by VRX equal to VS, meaning V supply, times RX over RTN. So that's your voltage divider. So if you have resistances connected in series, you have resistances connected in series, and we want to find the voltage across any resistor. Then it is the supply times that resistance we are interested in, divided by the total resistance. All right? For your parallel circuit, and we restrict this to 2 resistances. You can do it for more, but we are going to encourage you to avoid errors that, we just stick to 2. Here we have that IT is equal to I1 plus I2. We also know that I1 is equal to E over R1. Okay? Also, RT, or we go back to 1 over RT, let's start from there, is equal to 1 over R1 plus 1 over R2, which implies that RT is equal to R1 times R2 over R1 plus R2. Yes? And from what we had indicated before, IT is equal to E over RT, which implies that E is equal to IT RT. Yep. Do we have this? All right, so making the substitution for E in that equation, yes, we know that I1, as I said before, is equal to E over R1, but E, based on what we have, is equal to IT RT. So we have IT RT, yes, that is E, and we're dividing that by R1. But RT, as we just showed, so we have IT over R1, and RT is R1, R2 over R1 plus R2. So of course, R1 cancels with the R1 there, and we get I1 to be equal to IT R2 over R1 plus R2. This is known as the current divider rule. All right. Remember, I am encouraging you to restrict it to two resistances. So this implies that I2 would be equal to IT R1 over R1 plus R2. All right. Simple application. What we're saying is that if you're dividing current between two resistances, then it is the total current times the other resistor. So if you want the current through R1, then it is the total current times R2 over the sum. All right, so it's times the other resistance. Okay? All right, so we have gone through all these preliminaries. We have looked at voltage divider rule. We have looked at current divider rule. We have looked at how to determine power supplied, power absorbed. We completed the whole thing on parallel circuits. So let's put all of what we have learned since last week together and do some circuit analysis. Okay? Any questions? All right, well, add this to your thoughts, eh? Okay, so you can review that when you look at the recording. So let me formally now give you the two statements that we gave earlier. We said that series connection, resistances are considered to be in series if the current leaving one resistance, yes, and remember, I'm deliberately using the term resistance. But we're not always gonna be talking about resistors, right? But you'll see that in a few. Leaving one resistance is the same entering the other. Good. And parallel, resistances are considered to be in parallel if the current entering the node connecting them divides between them. All right. And when we're dealing with especially with the parallel, we want to take no more than two. All right. So, ladies and gentlemen, take the circuit from me quickly. Okay, so we have a circuit here. We have 5 resistors connected. We have a current IT leaving the source. All right, and our task is to determine which resistors or resistances are in series with which. All right, and we said earlier that we are going to use the current flow, yes, to indicate what is happening. So we start with our current IT. So the current IT leaves our source. No argument there. The current flows through R1. Yes? What happens to the current after it passes through R1?
So it shares between R2 and R3.
You see R2 and R3 on the screen?
Nothing happens, sir.
Nothing happens. It stays the
Nothing
same.
happens.
No, man, something happened, man. But I'm saying, based on what you see on the screen,
Okay.
R1, the current passes through R1. What happens to it?
The circuit.
It goes into that big orange box. That's what's on the screen. Is that so?
All right, sir.
And what's on the screen represents, as Mr. Denham just said, the rest of the circuit. So what we can say, let me not make a statement. Let me ask, Mr. Denham, based on what you just said, how then is R1 connected with the stuff in the box?
series
Why?
because the current leaving R1 entering the box, like the same current.
Same current. Keyword, the same current. All right? So R1 is in series with everything else. Let's move on. IT now enters that node. Are we agree it's a node? What happens to the current?
Splits.
It's our shared.
It splits. All right, that's one way.
It's
Splits how?
it's now being shared between
like that.
R2 and the orange box, which is the rest of the
Red box.
circuit.
Thank you very
The
much. So
red
the
box.
current divides between R2 and the orange box. So what can we say?
R1 is parallel to R2 and the orange
You get
box.
R1 in parallel. Come on.
R2 is
R2 is parallel with the orange
Yeah,
box.
yeah, yeah.
Thank you
R2 is
very much.
parallel.
All we can say at this point is that R2 is in parallel with whatever is in the orange box. Step by step, keeping it simple. And of course, by Kirchhoff's current law, the current entering the node is IT. If I2 goes through R2, then of course IT minus I2 would go to the orange box. Agreed? All right, next. That current goes through R3. And what happens thereafter? Come on, talk to me.
It is
It
the
goes
same.
into the orange box.
Current goes into the orange box with the rest of the circuit.
And therefore we can say, Mr. Clark,
That R3 is in series with the remaining circuit.
beautiful. Do we have another node there? So we have another node here. I thought they got,
The
yes, Mr.
current
Gibbs.
from R3 is the current from R3 is now being shared between R4 and the rest of the circuit.
Therefore,
It's in parallel.
what?
R4 is in parallel to the rest of the circuit.
Thank you very much. All right. And then that current would pass through R5. So I have analyzed the circuit, just looking at how the current is flowing. Yes? Now, if we were going to simplify this circuit, the principle in terms of analysis is that you go away from the source. But in terms of circuit reduction, we work towards the source. Yes? So working towards the source, I would start at R4 and R5 and combine them as a single resistor. Because remember, in your analysis, all you said, or what you said, was that R4 was in parallel with R5. Those are the only two resistors that you can combine immediately. You agree with that? So if you
Yes.
combine these two, you get a single resistor. Now, that combination, based on what you said earlier, was in series. So this is the combination. Let's call that combo one. Combination one. That's when R4 and 5 are combined. Yes? You now have R3 in series with that combination. Everybody with me? I haven't lost anybody. If I have lost you, please speak up.
Yes, sir. Yes, sir.
Yes, I have lost you.
No, sir. No, sir.
Okay, just checking. All right. So R3 is in series with that combination. And so we get now the previous combination, which we know was in parallel with R2. We're still doing circuit reduction, right? And then finally, we know that everything that we have combined is in series with R1. But students, what if, I mean, we're at university, we must get learn something new now. I want you to write down these designations. The designations are the plus sign, series connected. Parallel lines, parallel connected. Brackets are going to represent rest of the circuit. So this is how we are going to apply it to what we just, to the circuit we just looked at. Yeah? Are we ready? This is how we're going to apply it. Remember now?
1 minute, sir. 1 minute.
Okay, no problem.
Okay, sir.
All right. Where are we? 11:50. Okay, that's good. Now the circuit that we just looked at with R1, 2, 3, 4, and 5. Yes? We're going to write, as I said just now, the resistance equation. And every time I use the word series, every time I say series, I'm going to write a plus sign. Whenever I say parallel, I'm going to put some parallel lines. Whenever I say rest of circuit, I'm going to open a bracket. How that sound? Not sound too difficult. So let's go. With my circuit, yes? Well, let me just redraw it. All right, and what we want to find is the total current. So the total current RT, total resistance, sorry. Total resistance RT is equal to, now, remember I'm looking at what's happening with the current flow. And we just went through the exercise. So the current leaving my source, what happens to it? What's the first resistor it encounters? R1.
R1.
So I write R1. And how did we say R1 was connected?
Series.
Series.
In series with, so when I say series, I put a plus sign.
Rest of the circuit.
Yeah?
I put
And then it's in series with
Rest of the
Source.
circuit.
rest of the circuit. And so we put in, we open a bracket. Remember what we said we were using? Every time I say series, I put a plus sign. Every time I say rest of circuit, I open a bracket.
Yeah.
When I say parallel, I put in the parallel lines. All right? So R1 is in series with the rest of the circuit.
Yeah.
R2, next resistor we encounter is R2. So I write R2. How did we say R2 was connected?
Parallel.
Parallel. So I put my parallel, my two lines. And it's in parallel with
Rest of the
Rest
circuit.
of circuit.
rest of the circuit. So I open another bracket. What's the next resistor?
R3.
R2.
And how is it connected?
Series.
So we put plus, and it's connected in series with.
Rest of the circuit.
Rest of
So I
the circuit.
open another bracket. What's the next resistor?
R4.
R4. And how is R4 connected?
In
Parallel.
parallel with R5.
Parallel with R5. I have no more resistors, so I just close the brackets. And that, ladies and gentlemen, is what we refer to as your resistance equation. Now, I know you got, in my days we used to talk about new maths, but I doubt the maths has changed that much. In terms of dealing with brackets, Mr. Vassal, what's the rule?
BODMAS. That's what you refer to?
I don't know if I say it, but when we deal with brackets,
BODMAS or BOMDAS.
when we're dealing with brackets, what do we do?
I don't understand. We expand the bracket.
Yeah, I'm having some brackets here. How do I treat with it?
Oh, we work the bracket first. So
I
we
work
work
the
from
bracket
the
first.
inner bracket first.
Oh, that not coming away to that cost me out a while ago.
Cause you, I don't understand.
Then them words then up. Oh, is an acronym?
Yes.
Oh, I see. But we know deal with them acronyms around here, Mr. Vass. So we deal with the innermost brackets first, no?
Yes.
Good. Now, Mr. Vassal, I'm sticking with you. In dealing with the innermost brackets first,
Yes.
I would have dealt with resistors R4 and
4
5.
and 5.
Yes. You remember when we were doing the circuit reduction? When we were doing the circuit just
I
now.
believe. Okay. Yes. I
No, you
remember.
don't remember.
I
man.
was late, but yes. We can continue.
I was looking at you. You were sitting right there.
Okay.
Unless it was between wings. I don't know. But anyway, R4 and R5, when we were
Yeah.
reducing the circuit, that was at the end going towards the source. No, so.
Yes.
So dealing with the innermost brackets and dealing with R4 and 5, I would have been reducing those two resistors into a single resistance.
Yes.
And when I get that result, I then would have R3 in series with whatever was in that bracket. Because we're dealing with
Yes.
innermost brackets first, no? So it
Yes.
means I would have now dealt with R3. And
Yes.
then I would have R2 in parallel with a resistance.
Yes.
And then dealing with that bracket, I end up with R1 in series with a resistance. The point,
Yes.
the key point here, students, if you look at what we have done, at no time will you have to deal with more than two resistors or two resistances. And I submit to you, based on what we did earlier, anyway, I can't go back up there. But remember, two resistors in parallel. What's the quick formula that we just showed? Product over sum. So you have the two, you just multiply them and divide them by the sum. So at no time will you have to deal with more than two resistances. Of course, if they are in series, adding the two of them is quite simple. Fair enough? Any questions before we do a problem? Any questions?
No, sir.
Mr. Rogers, how you so brave? You know what me gonna do now, right? Okay. And it's a saved by the bell. All right, come. So we now move to doing a question. So I'm gonna use the same circuit in terms of the elements, and we want to find the total resistance for this circuit. All right, so let's begin. Let me volunteer somebody, huh? So Walker, Alan Walker.
Yes, sir.
All right, let's go through this together.
All right, sir. So we know that the 4 ohm resistance, well, going through it again, sir.
So RT, give me the equation.
Yes. So RT equals 4 ohms in series with brackets 9 ohms, which is in parallel with brackets 8 ohms, which is in series with 15 ohms, brackets 15 ohms, which is in parallel with 30 ohms. And then we can work with 15 and 30 ohms in parallel.
Thank you
So-
very much. Thank you, Mr. Allen.
Okay.
All right. Does anyone have an issue with what Mr. Allen just said? Anybody not understanding or didn't understand what Mr. Allen just did? All right. Okay, so we're now going to reduce this in order to find the total resistance. All right. And we're going to do everything, in one place. So
Excuse me,
let's-
sir. Do we have to show all working, or in the simple format we could just calculate and we would get the compute as is, and then we would just put our answer? Or do we have to show all working?
Let's do it first and then you ask me that question after. All right?
Okay.
All right, no problem. So let's do the reduction. So we start with the 15 and the 30. So we have product over sum. So 15 over and 30, product over sum, what is that? 10 ohms. So we get 10. And then I have the 10 and the 8. Those are in series. What does that give us?
18.
Beautiful. And then I have the 9 and the 18. What does that give us?
6.
So that is product over sum. We get 6. And then I have the 4 and the 6. That gives me?
10.
All right. Everybody with me? So what we have shown here is that at no time will I have to deal with more than 2 resistances. Also, I don't have to redraw the circuit several times. I have the equation, and I have written them down. Yes? Any questions? The total resistance we're finding. Nice and simple. So the question Mr. Vassler asked regarding whether I want to show working. I mean, I've asked for, total resistance. Not much to it. I would expect that you would show me the equation. And if you want to just drop the last answer, it's up to you. All right. I ask the question again. Does anyone have any questions? Or is it crystal clear? All right. So take this question from me. All right, so we have a time crunch, so we need to get back here. Okay, so the question asks us to find the power dissipated by each resistor and the power supplied by the 30-volt source. So in order for us to find the power dissipated by each resistor, Mr. Horn, what will I need to calculate? What will I need to first calculate? Horn?
The current.
What current? All right, Mr. Campbell, what do I need to determine in order to find the power dissipated by each resistor?
For this, sir, so basically you're going to find the total resistance first.
No, man, I don't want the process. I ask you, what do I need to determine in order to find the power dissipated by each resistor?
Oh, just the total resistance.
All right, maybe my questioning techniques are
Yes, sir, because-
faltering. Let me try again.
Yes,
So
sir.
forward.
Yes, sir.
I am asked to find the power dissipated by each resistor. What do I need in order to do that?
The polarity of the
I want the current, the power in each resistor. What do I need? What information do I need in order to find the power in each resistor?
current and voltage. What's it called?
Current, well, we can use, since we have the resistances, we can find either the current or the voltage, yes?
Yes.
That's all I'm asking. So we need to find the current through each resistor. All right? So that is our objective. The question now is, how do I go about doing that? Fair enough? So the first step, ladies and gentlemen, the first step is for us to determine the total resistance. And I'm going to write the resistance equation for this circuit. Let's see, who's going to do that for us? Mr. Small.
Yes, sir.
Come, resistance equation.
Okay, so you're gonna have RT equals 3 ohms plus open bracket 14 ohms, parallel lines, open bracket 4 ohms, parallel lines. Parallel lines again, sir. 2 parallel lines. 4 ohms plus 2 parallel lines. And the parallel lines after.
So the 4 is in parallel with the rest of the circuit?
Oh, series. Oh, sorry. Series. Oops. Open bracket. 15 ohms. And this is in parallel with 23 ohms, which is in series with the 7 ohms.
Thank you, sir. All right. Who's next now? Gordon, Duane?
Yes, sir.
I want to simplify.
All right, sir. So we go for the product of by some rules, sir. So it's say 23 plus 7 over. That's a plus, sir. Yes. That would be
It's 23 plus 7 now.
oh sorry, sir. I thought we were going to do the product over some rules, sir.
But the
that
23
would be the 30,
the 23 is in series with the 7.
Yeah, that's what I'm realizing, sir. That would be a 30.
Okay. So the 30 and the 15 in parallel.
1 second, sir. Yeah, 10, sir.
The 10 plus 4.
14.
The 14 is in parallel.
Yes, 7, sir.
And the 7 in series with the 3.
10.
So RT is equal to 10 ohms. Is there anybody who is in disagreement with this? All right. So with RT being 10, it implies that our current I is equal to V for RT, which is 30 over 10, which gives us 3 amperes. All right. So I'm going to use the opportunity now to the question was asked earlier by Mr. Vaso, yes, about whether or not you want to show working or or you just want to throw the answer at me. We want to know, show the benefit of having this information before us and working it and showing it step by step. Yes, Mr. Small.
Sir, after this session, will you be uploading the notes to school?
I don't believe you're not going to break me and ask me that. No, Mr. You're serious? No, man, don't ask me those questions. I dealt with that in my opening lecture. I spoke about all those things. You just take the notes right now. As a matter of fact, when people ask me those questions, I am more inclined not to upload. So let's just focus and write the notes. Going back to the circuit, we're going to take the resistors one by one, okay? Now, this 3 amperes, all will flow through the 3 ohm resistor. Agreed?
Yes, sir.
So for the 3 ohm resistor, I'm going to call it IR3 ohm or I3 ohm. I'm just going to use the resistors as a subscript, okay? So I3 ohm is equal to IT, which is equal to 3 amperes. So all the current flows through the 3 ohm. Now let's go back to the equation. We said that the 3 ohm was in series with the rest of the circuit. Agreed? So it means that all the 3 ohms will go to the rest of the circuit because they are in series. Isn't that so? Now when it gets to the node.
The 3 amps, sir.
Yeah, the 3 amps. Thanks. Thank you. Thank you very much. When it gets to the node, what happens? Look at the equation. What happens? It divides between what?
The 14 and the rest of the
The
circuit.
rest of the circuit.
And if you look in your solution that you have written down, you can quickly determine what the resistance was for the rest of the circuit. It was 14. From the resistance equation, the rest of the circuit was 14. Agreed?
Or 7, sir.
No.
Oh, 14.
It's 14 in parallel with 14 that gave you 7. Go back to the circuit. This is the 14 ohm,
Yes, sir.
and it's in parallel with everything back here, which
Oh,
is
right,
also
right.
14.
Yes, sir.
Right? So I'm
Yes,
saying
sir.
I'm not even looking back at the circuit. You know. I'm using what I have written in terms of the resistance equation to do the analysis.
Yes, sir.
You with me?
Yeah,
So
I
in
got you.
looking back, I'm seeing that 14 is in parallel with 14. So I can now write that I14 ohm would be equal to IT, which is 3, times 14 over 14 plus 14. And that gives us 1.5 amperes. So for the 14 ohm resistor, we have 1.5 amperes. Let's go back to the circuit, to the equation.
Yeah.
Huh? The current going into the rest of the circuit, which resistor does it pass through? I mean, after it divides between the 14, it passes through its resistor.
4 ohm.
4.
4 ohm, which implies that I4 ohm would be equal to IT minus I14, which is equal to 3 minus 1.5, which gives us 1.5 amperes. Everybody following me? Have I lost
Yes.
anyone?
No, I see that this before.
All right. So we now have 1.5 amperes going through the 4 ohm. Yes? If we look back at our circuit, the next resistor we are dealing with is what? 15.
The 15 ohm.
No, the 15 is in parallel with what?
So the rest of the circuit.
Circuit.
And you come back to your equation and you see that it is what? 30. So the
30.
rest of the circuit is 30.
Yes, sir.
So you come back and you write I15 is equal to the current passing coming towards them, which is 1.5, times the other resistance, which is the rest of the circuit, 30 over 15. And that gives us 1 ampere. So there you go. 15 plus 30. Sorry, my
Plus
mistake.
30. Yeah,
15
yeah.
plus 30. My mistake. That gives us 1 ampere. Next resistor is a 23 ohm, which is equal to I15, I4 minus I15, which is 1.5 minus 1, which gives us 0.5 amperes. So the current flowing to the 23 ohm would be 0.5. Everybody agree with that? And then you come back to your equation, and you look at the equation. How is the 23 connected to 7?
Series.
They're in series. So it means therefore that I7 ohm is also
to
equal to
0.5.
0.5. Because it's in series with the 23. And how long did it take us? 3 minutes? In a few minutes, you have all the currents through all the resistors. Now, students, remember we talked last week about confidence. Don't feel any way that, we took 3-4 minutes to do it. Don't know. I guarantee you that with practice, you'll be able to do this in a few seconds. So now that I have the currents, please go ahead and find the power dissipated in each resistor for me. Okay, P3 ohm.
$27.
P14.
Uh, 31.5.
P4.
9 watts.
9 watts, sir.
Okay, P15.
15 watts.
15
watts.
15 watts.
And P23.
5.75 watts.
5.75.
And P7.
1.7. Yeah, 1.75.
Okay, so add these up for PT.
What?
All right, and the question had asked us to find the power dissipated by each resistor and also the power supplied, yeah? So from the circuit, the supply voltage is 30. Yes, so the power supplied is equal to VI, which gives us 30, and that would be IT times 3, which is 90 watts. And as I said before, we can determine whether or not our analysis is correct by looking at the power balance. So the power supplied here is 90 watts, and we have confirmed that by calculating the power dissipated by the resistors to also be 90 watts. Okay? Does anyone have any question relating to what we have just done? Any questions? Oh, we're good. We're good? We're all good with this? Someone, you good with this? All right. Okay. So, since we had deafening silence, please take this question. And this must be submitted by tomorrow at 8 a.m. All right? So you're gonna complete that. And you're gonna submit it by 8 tomorrow morning. Discuss for a few minutes your approach to this question. No, you don't have to worry about what analysis techniques we would have used. Of course, you're seeing that we have introduced or put in a number of sources, but that's not important. That's not critical. What I wanted to be able to do is to apply all that we have dealt with since last week, because this is more or less a culmination of all that we have done. So in order to find power for any source, for a source, what bit of information will you need? You want to find power for a source, what do you need?
Current and source voltage.
Okay. Now, I'm not sure who said it just now, but he said current and source voltage. Is that what was said?
Yes, sir.
Okay. So that was you, Mr. Bernard?
Yes, sir.
All right. So what do you do with this then?
So I'm not
If I want the
really
power
sure.
for that, and that's a current source, what do I do?
Not really sure, sir.
Sir, find the voltage across it, sir.
All right. So I deliberately asked because you see immediately you start to talk about source voltage. It's clear that you're looking back or you're depending on what you already know. And I've warned you about that before, Mr. Bernard. It's the last time I'm going to warn you. All right? But usually I give students enough rope. But I would prefer not to do that, Mr. Bernard. That is why I'm picking on you, because I don't want you to make the mistake that so many students continue to make with this module. So,
Okay,
Mr.
sir.
Campbell, you're saying that you find the voltage across it, eh?
Yes, sir.
So instead of using the terminology current and source voltage, for any source, what you need is the voltage and current information. So if you have a voltage source, you want the current through it. If you have a current source, you want the voltage across it. All right? Now, so obviously you'll do that for these two sources. The next thing is that how do you then determine whether or not a source is delivering power as against absorbing power? Because remember, when we spoke about the two car batteries, one was delivering and one was absorbing. Good? But those are two voltage sources. So I want to know a general statement that helps us to determine whether we have a source that is absorbing power or one that is delivering power. How do we make that determination?
Sir, can I repeat the question, please?
For a source, right? How do you determine whether or not it is delivering as against absorbing power?
Sir, I think you
Sir,
look
the
at
source with the highest potential is delivering the power, and the source with the lowest potential is absorbing the power.
yes, sir. So, yeah.
Okay, so tell me now, how many sources you see in this circuit?
Two sources. Three
Five.
sources. No, four sources.
Five
There are
sources.
5 sources.
So there are 5 sources, yes? So let me use what Mr. Martin just said. Which of these sources has the highest potential?
So you can't really tell that, sir.
Exactly. You can't tell. Right? I mean, yes, if you want to say 20 volts, you really don't know. What if it was the 3 amp source? So obviously, that method would not be foolproof. You with me, Mr. Martin? So let us discuss it again. How do we determine whether or not a source is delivering power as against absorbing power?
So you'd have to look at the
Based
polarity.
on the flow of the current and how it enters the source.
Enters the source, but it could be leaving the source. All right, go again, Miss Sam. Go again.
So I'm saying that based on the current flow, right?
All right.
And I said, it enters the source, whether it enters the positive terminal or it enters the negative.
Okay, that's what you meant. All right. So for a voltage source, how do I know that it is delivering power?
For a voltage
Sir, the move
source,
from the positive, sir.
So the current is leaving the positive. So for voltage sources, they are supplying power if the current is leaving the positive. Now, earlier, Mr. Campbell said that in order to find the power supplied by the current source, you would need a voltage across it. Agreed? That's what you said, Mr. Campbell.
Yes, sir.
I don't want to misquote you, so I want you to confirm. All right. Now, when I find that voltage as we have defined it, yes, a voltage is defined as, Mr. Campbell?
Sir, a voltage is defined as difference in potential between 2 points.
Okay, so when I find the voltage across, let's say the 2 ampere source, I would have potentials at either end.
Yes, sir.
Because, it's a voltage, so one side must be plus or one minus.
Yes, sir.
So let us say when I find that voltage, this has the higher potential. So I have plus minus. Is
Yes,
the 2 amp source, if it was plus minus, I'm not saying it is, because I don't know. I don't know. I just set these questions. I don't know the answers. All right. If it was a plus at the top, would this 2 amp source be delivering or absorbing power?
So it depends. It depends.
No. It depends on nothing. I am saying, if when you have found the voltage across the source, yes, it turns out that at point B, you have a higher potential than at point A.
Yes, sir.
So in other words, the voltage, the higher potential, well, there's no other way to say it, right? The higher potential is at A as against B. At B as against A. Would the 2 amp source be delivering power or would it be absorbing power? That is
Delivering power.
Delivering. Because the current is flowing from the higher potential of the source. All right. So for this question, which you are going to add to the one I gave you earlier. Yes. So you have 2 questions now to submit. For this question, you are going to be applying Kirchhoff's current law. You're going to be applying the principles we outlined in terms of voltage rise, voltage drop. You're going to apply, what else? Yeah, that's about it. So this question is a perfect summary for everything that we have done since last week. All right? Once you have done that, then next time we meet, we'll take it to another level. Okay?
Sir,
Yes, Mr. Denham.
for question A, it mean the voltage across each component?
Oh, you mean part A?
Yes, sir.
That's one way of saying it.
All right, thanks.
All right. Please note the nodes that are on the circuit, yeah? Okay.
Sir, I have
Let's
a
see.
question.
Mhm.
Do you have any idea how our practical class is going?
I sent you all some information yesterday. I
Yes,
said I
sir.
communicate with, pardon?
Do you have a contact to
It's in there. Did you read the message I sent you?
message, but I don't see a contact to her.
Well, I'm absolutely sure it's there. Read the message. Everything is there. All righty, let's see, I'm gonna go through, I'm just gonna go through the list here. It has both classes. I wanna separate you guys, but for now. All right, Alexander, Alan, Richard, Atkins, Joshua.
Yes, sir.
All right, Barnett, Jamar.
Yes, sir.
Okay, Bernard, Rahim,
Yes, sir.
Bogo,
Yes, sir.
Wayne Bogo,
Sir, here.
Wayne Bogo. All right, Burkett,
Yes, sir.
Campbell, Jordan, Zachary Campbell, or Zachary
Yes,
Campbell,
Yes, sir.
Case, Chamberlain, Chambers, Maliki, Clarkey, Devon,
Yes, sir. Yes, sir.
Codling, Gabriel,
Sir.
Codling,
Yes, sir.
okay. Denham, yes, Ellis, Rowan, Farrell, Ford,
Yes, sir.
Freighter, Matthew, Gardner, Hakeem, Gibbs, Jean,
Here, sir.
Gordon, Dewey,
Yes, sir.
Halstead, Joshua,
Yes, sir.
Harris, Son, Jamo, or Jomo,
Yes, sir. Yes, sir.
yeah,
Yes, sir.
Hales, Matthew,
Yes, sir.
Matthew Hales, George Henry, Javoy Henry,
Yes, sir.
Hopkins,
Yes, sir.
Horn,
Yes, sir.
Johnson, Jonathan,
Yes, sir.
Kelly, Romaine,
Yes, sir.
Lawrence, Akeem, Levine, Danielle, McIntosh, Josh David,
Here, sir.
Miller, Leron,
Here, sir.
Moffat, Dimitri, no, that's Monday night. Morgan, Shamar. Maurice here. Chanel on Friday, that's Monday. Ramsey, O'Neill. Samuels, Jerome. Sinclair, Carlington. Skyers. Skyers. Small, DeAndre.
Present, sir.
And Marlando Small. And Smelly, Everton.
Present, sir.
And Smith, Jamil. All right. That's it. It's now 1 o'clock. Have a good afternoon.
Sir, I didn't hear my name.
My name was
Yes, sir. I didn't hear my name either.
Same.
Let's see. Oh, there's more. Oh, God. All right. If you have already heard the name, you can leave. Sterling Adili. Rolandino Sterling.
Present.
Rajan Stevens. Okay, Mr. Thomas Olandre. David Thompson.
Yes, sir.
David Thompson. Calvin Vassell.
Present, sir.
Alan Walker. Alan. Walker.
Present, sir.
Garnet Williams. Romano Williams. Sherwin Williams. Daniel Wilmot.
Yes, sir.
Daniel Wilmot.
Yes, sir.
Okay, Brandon Wilson. And Oraldo White. Right, sorry. All right, so yeah, that's it. So that means, man.
Sir, I didn't hear my name, sir.
Yeah, well, I accepted everybody up to last night. So if you sent it in this morning, I wouldn't have it.
All right, sir.
Okay. All right, that's it. Take care.
All right, sir.
All right.
Sir,
Yes.
sir, should we submit the practice questions you gave at the end of last week class
Pardon me?
tomorrow as well?
Pardon me?
The practice questions you submitted at the end of should we submit the assignment tomorrow?
I'm not hearing you.
The two questions.
I gave you 2 questions for submission tomorrow.
But then can you hear me now?
I'm saying I gave you 2 questions for submission
No,
tomorrow.
man, not the ones you gave.
That's all I have given for submission. 2 questions
not the one
today
you
for
gave
submission.
Okay. All right.
All right. So
All
I'm
right.
saying I gave you
That's
2
fine.
questions today for submission. That's it.
Sir.
Yes.
I joined like at the last part of the class because I have a clash with math. So I knew like this is my first class.